Hey everyone, welcome to The Explainer. Today we're diving into some pretty unexpected behaviors in Python. We're going to explore how it handles operator overloading under the hood, and then expose some notoriously sneaky hidden interview traps. Whether you're building massive data pipelines or just prepping for your next big technical interview, you really need to know how Python is managing memory behind the scenes.
Here's the game plan for today. First up, we've got the magic of operator overloading. Then we'll tackle the Python interview grid trap. After that, we're looking at mutable binary with bytearray, and we'll wrap up with the replace method pitfall. Let's get into it.
Starting us off, Section 1, the magic of operator overloading.
You know, Python is famous for feeling really intuitive, and a huge chunk of that comes down to this core concept. Operator overloading is basically giving a standard operator a different but analogous meaning when you use it with a specific data type. I mean, you already know what the plus sign and the multiplication star do in numbers, right? But Python actually overloads these mathematical operators so that working with lists feels just as natural and elegant as simple arithmetic.
So let's look at the distinct behavior of these two overloaded operators. When we use the plus operator on lists, it concatenates them. It literally stitches them together. But here's the absolutely crucial part. It creates a completely new list. Same thing goes for the multiplication operator, the asterisk. It repeats a list n times, and again, creates a brand new list. The underlying secret here, the big takeaway, is that the original lists you started with, they are completely untouched.
Let's actually trace through an example together. Say we have a base list with water and milk, and a flavor list with ginger. When we execute base plus flavor, we get a totally new list called mix with all three items. But if we go back and print our base list again, it is strictly unchanged. It is still just water and milk. The plus sign didn't modify either of the original lists, it birthed a brand new one. And the exact same rule applies when we multiply. Multiplying a list by 3 just spits out a new list with that pattern repeating 3 times. It's clean, it's safe, and it's totally predictable.
Which brings us to Section 2, the Python interview grid trap.
All right, put your interview hats on for this one. Take a really close look at this short snippet. We've got a list containing a 0, multiplied by 3, and all of that is nested inside another list and multiplied by 3. Now, at first glance, this looks like the perfect, elegant way to create a 3 by 3 matrix of zeros, right? So, what could possibly be the danger here? I'll give you a second to think about it.
Got it? Well, here's the underlying issue. All of those rows are pointing to the exact same list object. Because lists are mutable in Python, when you tell it to multiply that inner list of 3 zeros by 3, it doesn't actually create 3 independent rows. Nope. It just creates 3 references pointing to the exact same location in memory. So if you try to update the top left corner of your grid by assigning a new value, you aren't just changing the first row. You're changing the underlying object that every single row points to. Suddenly, your entire left column updates. It's a massive bug and a total classic interview gotcha.
So, how do we fix it? Well, instead of that anti-pattern, you want to use the correct Pythonic approach, a list comprehension. By writing out a loop inside the list brackets, you are forcing Python to execute that inner list creation 3 distinct times. This guarantees that you get 3 entirely independent rows. You can modify one, and the others are going to remain safely untouched.
Moving right along to Section 3, mutable binary with bytearray.
Typically, when you're working with text in Python, you encode a string into standard immutable bytes. But what if we want to manipulate raw binary data and actually alter it on the fly without decoding it first? That is where we use a structure called a byte array. A byte array is essentially a sequence of integers ranging from 0 to 255, where each integer represents exactly 1 byte. But the absolute most important word in that definition is mutable. This is the flexible, editable counterpart to the standard frozen bytes object. Comparing standard bytes directly to a byte array really clarifies when to use which. Standard bytes are immutable. They're frozen. You can't index assign to them, which makes them perfect for fixed binary data or, say, dictionary keys. But a byte array is fully mutable. You can dive right in and say, hey, change the data at index 0 to the number 72. And why does this matter? Well, imagine you're editing a massive binary file or processing a constant stream of network buffers. You definitely don't want to spin up a whole new multi-megabyte object just to flip a single bit. You want to edit it right there, in place. That is the superpower of the byte array.
Let's see how this actually looks in the code. If we create a byte array with the binary word cinnamon, because it's mutable, we can access the first byte directly by its index. The raw array at index 0 equals 67. And 67, by the way, is the ASCII code for a capital C. We can also jump over to index 4 and assign it 65, which is the ASCII code for capital A. It directly overwrites that exact slot in the binary sequence. It works perfectly, and it allows you to do these really surgical strikes on your data without any massive memory overhead.
But beware. That brings us to section 4, the replace method pitfall.
There's a crucial, honestly kind of counterintuitive rule here. The replace method returns a new byte array. You absolutely must reassign it. Since a byte array's entire purpose in life is to be mutable, you'd naturally assume that calling .replace would edit the contents right there on the spot. But it doesn't. It actually behaves exactly like strings do. It generates a completely new object.
If you just run that replacement method on its own, the replacement does happen, but the result is instantly discarded into the void because you didn't catch it. Your original byte array remains completely unaffected. To actually apply the change, you have to reassign it. You have to explicitly say your variable equals the variable .replace. It is such a small detail, but forgetting it, that's going to cause completely silent failures in your data processing.
All right, time for a quick flashcard challenge. Let's lock in this knowledge and make sure these memory mechanics are really sticking.
Question 1. Think back to the very beginning of the explainer. What exactly does list1 plus list2 do in Python? Think about what's happening with the memory.
The answer, it creates a completely new list. It takes the elements from both, stitches them together into a fresh object, and ensures that neither of your original lists is modified in any way. Safe and predictable.
Okay, question 2. Testing that final trap we just looked at. What does the bytearray.replace method actually return?
It returns a new byte array. Despite the object itself being mutable, the replace method does not modify it in place. You absolutely must reassign the result to a variable, or your changes are literally lost forever.
Which brings us to our final thought for today. Now that you understand the mechanics of operator overloading, the very real danger of shallow reference copies, and the quirky rules of mutable byte arrays, can you spot the memory reference traps in your own code before the compiler does? I challenge you to open up one of your current Python projects today and just take a look at how you're generating lists and handling mutable data. You might just find a bug hiding in plain sight. Thanks so much for joining me for this explainer. Keep learning, keep coding, and I'll catch you in the next one.